Okay, so let's go ahead and get started. I know that a few of you, well, I think a couple of you emailed me asking about some of the stuff from yesterday's lecture. So I'm just going to go ahead and start off with, let's go over the implications and the conditional statements that we talked about yesterday, and we can talk a little bit about. I'll probably give you an example. Yeah, I think I'm just going to be the way to do it. I'll give you an example to kind of like see what it means to be true in a truth table, sort of, with regards to the statements. And then there's one small thing I want to segue into while talking about propositional, and then we'll probably just finish up the section on propositional logic. So in the homework that I sent out yesterday, there are a few questions that you would notice we haven't really covered yet. You might look familiar to you just because we've talked a bit about negations, we've talked a bit about converting from English to predicate logic, but there's a few more things we have to talk about just to make sure we are finishing basically the formalism. So a lot of you asked me about the implication, the conditional statement. So let's just have our truth table again, and I'll just write out the truth table for P implies Q. Right. So we said yesterday that the only time this is false is if P is true and Q is not true, right? And that should make sense. The thing that a lot of people struggle with is why these two are true. And the best way to think about it is we just want to think about it as a case where when we look at this column, true just means, oh, this can happen, right? We're allowed to live in a world where this happens and whatever conditions were for this row, we're still fine, right? So false being that there's no way these could have like intersected. So instead of just looking at this statement, we kind of just look at the intersection of the row and the column. So for instance, let's use a concrete example here. P is a statement that it is raining, and Q is a statement that the ground is wet outside. Right, so I picked this so that you can kind of make sense of it, and we can kind of look at some examples and counterexamples. So, for instance, the first row is pretty self-explanatory, right? We're kind of like intersecting this, right? So if I live in a world where it is raining and the ground is wet outside, there's nothing wrong with the statement that if it is raining, the ground is wet outside, right? Or if it is raining, then the ground is wet outside. Let's kind of jump to the end here. It's possible for both of them to be false, right? If it's not raining, the ground is not wet outside, that's totally fine as well, right? You can easily imagine, well, if it's not raining, nothing's happening, the ground's not wet outside. Second row also isn't bad, right? If we have some open area, it is just totally not possible for it to rain and the ground just not be wet, right? The only way for it to not be wet if it's raining outside is if you've got some covering. So this is just not going to hold true. In other words, it's not possible to live in a world where P is true, Q is false, and P implies Q is true, right? So that's kind of what this false means over here. It means that we can't reconcile these conditions with the statement we are trying to make, right? So that's kind of the idea there. So the hardest one to understand is this third row over here, right? So kind of the way I talked about it yesterday was we talked about this being a vacuous statement that's vacuously true, right? So in other words, if P is false, then P implies Q is what we call vacuous true because we don't care about our conditions. We have no conditions to look at all. So essentially that's what's going on there. Now what about this case? So the idea is that let's try to live in a world where it's not raining and the ground is wet outside. Can this statement still be true? Or rather, is it possible to have this to be false and this to be true without breaking this conditional? Well, the idea is, I mean, sure, I'm just going to take a bucket of water, spill it on the ground outside. Look, it's raining and the ground's not wet. That's totally fine, right? It means that there's still a world in which we can create other conditions that forces this to be true, but that doesn't break this implication up here, right? And this is one of those ideas a lot of you who've taken statistics, or just in general, you've heard the phrase, correlation does not imply causation, right? So this doesn't mean that P is the only thing that causes Q to happen. It just means that if P happens, then Q happens. Maybe there's other things that could cause Q and stuff like that. So this doesn't break, right? So for example, if I kind of draw this small diagram here, right? So let's say P implies Q, and let's say I also have this other statement R that implies Q. It's totally possible for this to be false and this to be true because something else was true, right? So don't beat yourself up too much about trying to figure out, oh, do I have to create other conditions to force this to be true over here? You don't have to, right? It doesn't, as long as P is false, if this is the only statement you are examining, then we don't care about anything else. Now, when do we care about other conditions? The most common thing in math is by invoking the backwards direction, right? So that's why we say if and only if, or necessary and sufficient. In other words, when I say P if and only if Q, then that really restricts what I'm allowed to have, right? Both of them have to be true at the same time or false at the same time. So we can't really talk about cases where these kind of flip around, right? So then, now that we've talked about that, let's kind of just expand on this a little bit. We've got, hold on, let's see. Okay, so we've got this, which we call the conditional, right? Well, this is conditional statements. Right? We are conditioning that this is our hypothesis, this is our conclusion. So we have a condition that gives us Q, right? If we've met the condition that P is true, then we must have that Q is true. What about this? Let me go backwards. All right, this is one of the very common mistakes that people make logically, especially if they haven't taken math before, or maybe even if they haven't taken a science course before. A lot of people say, oh yeah, if this and that, they'll sometimes read it backwards, or they'll kind of just say, oh, if it goes one way, then it must go both ways. But that's not quite true. They're not really the same statement, right? So let's kind of give an example that P be a prime number that's greater than 2. Oh, sorry, this is not a statement. Let's rewrite this as a statement. So some number, let's call it x. We don't know what it is now. Again, this is not a variable because I'm saying that it's some number. I'm fixing it to be some number x. And Q is, I'll just say the same. There's some stuff in here I'm kind of neglecting and not being formal about, but y'all get the idea. Same number is odd, right? So if I want to read it as conditional, this essentially says that, you know, if I take some number x and it's a prime greater than 2, then that same x is odd. Well, that's obvious, right? Like 2 is the only even prime number. When I go further than that, everything else is odd. But the backwards doesn't work. if I just pick any odd number and fix it, right, it's not necessarily prime, right? 35 isn't prime because 35 is 5 times 7 and so on and so forth, right? So this is not always true, and you have to be careful about this. But we have names for each of these guys, right? So this is called converse. So as you're reading like math books, as you're reading proofs and stuff like that, a lot of people will say, oh, conversely, blah, 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 that's what this means, right? Conversely just means what happens when we're going backwards, right? And so when we prove a lot of if and only if statements where we're going back and forth, people will normally prove one direction and they say, oh, conversely, let's show the other way, right? That's why. Because once we remember from yesterday, our definition of P, if and only Q can also be written as this guy and this guy, right? We go both ways. You can immediately imagine what about this, right? If I just flip both of them. This is called the inverse. And finally, you can also flip this. You can take the converse of the inverse, and that's called the counterpart. Now it turns out there's a way in which you can pair these, right? We've already said that we want to avoid the major issue where we say the conditional and the converse are the same statement, because they're not logically equivalent using yesterday's language. But let's see if we can write up the truth table. Right, so if I look at Q implies P, right, we're going the other way, right? So this is the only case it's false, right? Remember, in a conditional statement, the only time it's false is if the premise or the hypothesis is true and the conclusion is false. So everything else is true, right? So now let's look at these other two statements. We've got the inverse and the composite, which deal with the negations, right? So let's make a new column for each of the negations to make our life a little bit easier. So we'll flip this, right? Dot P is the same as basically the opposite truth value of P, right? And then same thing for Q. And then we have not P implies not Q, right? So this is, in fact, remember, the only time this is false is if the premise or the hypothesis is true and the conclusion is false, right? So this guy is false, and everything else is true. And finally, we finish up here, same thing, right? True, false, that's the only time it's false. Every time else it's true. And now let's compare these last two columns with the last two columns over here. Let's compare it, right? Turns out these two guys. Do I have a color? Not right now. So these two guys are the same. They're logically equivalent. And these two guys are logically equivalent. Right? So we've got P plus Q. We've got F in the second row. Here we've got F in the second row for counterpart. So this is a very common thing, right? It's when if you find it hard to talk about the conditional statement, you can maybe look at the contrapositive instead, right? If my original statement has a bunch of nots in it, right? If I have a bunch of negations and whatever, and I don't want to deal with that, well, let's just flip everything. And it also sort of makes sense because we talked about De Morgan's laws yesterday, right? When we distribute a not symbol, we kind of have to distribute it everywhere. So it's almost this idea of if you flip one thing, you've got to flip everything at the same time. Same sort of idea, right? I've kind of flipped everything, including the direction of my arrows. Now, they're not negations of each other for reasons that we'll talk about in a little bit when we draw out some other ways of rewriting the statement, but that's kind of the idea. Right, so a lot of people, like, you won't hear the word inverse a lot. We don't really talk about this way, but it's good to know. A lot of people will either jump immediately to the contrapositive, or if we need to talk about the converse, we can talk about the converse, right? But we don't really look at this statement, but it's at least good to know that these are the names of these things that we generally talk about. This will come up pretty soon when we talk about proofs. There's obviously a lot of different names for different types of proofs. There'll be 4 major types of proof techniques I'll show you, one of which is proof by contrapositive, right? And that's basically from here, right? It's the idea that this statement, the contrapositive, is logically equivalent to the conditional. So if I have a conditional statement, one way to prove it, instead of directly proving the conditional, is maybe I can prove the contrapositive instead, right? If it's easier to do something like this, why not just do it, right? Because if I can prove this, that's the exact same thing as proving this, because they are logical statements. So one thing I want to say about this whole logical equivalence that we're talking about, it's good to know when 2 statements mean the same thing, but we also want to use that to our advantage, right? We want to say that, okay, if these 2 statements basically mean about the same thing, then something we can say it's enough to show that this second statement is true, or we can say it's sufficient to show that the second statement is true in order to prove that first one, right? You want to make your life easier for yourself. You don't always have to prove exactly the thing that you started with. You can just reword it as something else, and it doesn't even have to be just a paraphrasing or rewording. It can literally just be, oh, I'm going to rewrite this completely as long as I know that this is logically equivalent, right? So contrapositive is the easiest way to pick a logically equivalent statement that you have to prove. There's obviously other ways we can do it, but we'll go into that later. All right, so any questions here? Okay. So that's what I wanted to say about those 4 statements. And now let's talk real quick about how else we can write an implication, right? Because sometimes maybe we have a bunch of sets and we know something about these sets and what's in them, but we want to talk about kind of using the other using the other connectives, right? Because we have 5 connectives, and it turns out that, remember how I defined the if and only if as 2 different things put together? We can break that down further. We can express everything using only the first 3 connectives, right? So let's just look at P implies Q. I think we briefly mentioned this yesterday. If we look once again at the truth table for P implies Q, this is false, right? So what I'm about to do is let's see if we can find different ways of rewriting the statement in logical equivalent statements instead of like having to rewrite it algebraically as something else, like obviously you guys, I'm sure, have done stuff like, oh, you have 3 times x plus 4, you want to simplify, so this becomes 3x plus 12. These are the same statement because you did something to it, right? You can do that. But in this case, we can find logically equivalent statements using the truth table. So if we go ahead and look at the truth table here, well, what does it mean to be true? That means it's one of the cases, right? And all these cases are separate. Each of these are separate to each other. So maybe I can say it's true here and here and here, right? So that I can say maybe oh, sorry, I shouldn't use the word and, it's or, right? Because these are separate cases. So either this is true, or this is true, or this is true. They can't all be true at the same time, but it is one of those, right? So either P is true and Q is true, or P is false and Q is true. But what does it mean to be for P to be false? It means not P is true, or not P and not Q. But that's a lot, right? That's a lot to write. But you can almost imagine, well, instead of just talking about when it's true, maybe we can just say when it's false, right? And just do that, right? It's only false at one point. It's only false at the second row. So what does it mean to be false? We can stick a negation over all of it. Well, and what do we have in this case? We have P is true and Q is false. Right? So we have not P and not Q. But what if I don't want this negation outside? It's almost that idea of like, I don't want anything outside, I always want to distribute to simplify or something like that. So we can also find another logically equivalent statement here. Let's distribute this, right? You remember you can distribute this using De Morgan's laws, right? So I can write not P or not Q, or we can say not P or Q, right? So these are all equivalent statements here. We can say any of these things and be equally fine, right? So if we look at this, we've already said that by definition, when we apply the negation twice, you get the original statement. Otherwise, here, you don't have to touch it, right? And what I did from here to here, by De Morgan's laws, you just flip everything, right? It's P became not P, the and became an or, and so on and so forth, right? So these are all equivalent statements to the conditional. This is one we use most, like it almost looks like this is the most simplified, right? And a lot of times in my head, when someone gives me P implies Q, and I have to break it into cases, I usually think of it this way, right? But you can also see why this is true, right? I mean, we just look at what this means. It means either P is false or Q is true. Well, where is P false? P is false over here, or Q is true over here. So those are our cases, right? And maybe some of you as practice can maybe look at this statement and see if you can see why this, you can go immediately from this second statement all the way down here, right? Now, obviously, if I want to negate that, right, this is a good exercise just to see. This negation is obviously the negation of this, right? So negation sign goes away. This is the same as saying P and not P, right? So that's another set of equivalencies. So essentially, we're always talking about equivalencies just because we want to find different ways of representing our representing what we're trying to prove. Okay, so the last thing I want to talk about on propositional logic is just a couple of laws, right? So you guys know there's technically this was a law of the proposition that we talked about, where not Q is just by definition. We only define what not means, right? But by that definition, we can define not Q is logically equivalent to Q. There's some other things we can talk about. There's a lot of laws that you can apply just from the definitions. The main one I want to talk about is just distributive laws, right? So instead of just getting distributive laws, just me telling you how to distribute, let's go through one last example of a longer truth table. And I promise this will be the last example of like me beating the truth table horse to death. But just all practice on this stuff is always good to see, right? So what if I wanted to look at the statement P or Q, and I'll do this R outside, right? So you might almost wonder, okay, there's obviously a way to distribute this where you get something in R and P, and you get something about R and Q. Question is, what happens to these guys, right? You can almost see that this and symbol always goes with the R, right? So maybe I'm finding some way to combine R and P with R and Q, right? It's almost like I'm foiling this guy with here and this guy with here. The question is, what happens with this guy? And that's the one that goes inside, right? So that's kind of the intuitive way we can look at distributing, but if we want to prove it, well, the idea is let's do truth tables for both of these guys, right? And see that they're the same. And if you're not, so a good thing to do is, you should always use your intuition to try to figure out what's the same, right? You should try to use your intuition to figure out what you're actually talking about, but intuition is almost never enough, right? The main issue that a lot of people struggle with in undergrad mathematics is a lot of times people will build up a very good intuition for these types of problems. They'll build up a good intuition, a good picture in their head or something of the sort, and then they'll go for it, you have to prove basically everything, right? Intuition is never enough. Intuition helps you figure out whether you're on the right track, and it helps you keep track of things in your head. But it's never going to be, it's never something you want to rely on by itself, right? There's a lot of times I can give you some really weird counterexample, especially once we start talking about the analysis related topics. There's a lot of counterexamples you can come up with that are counterintuitive, right? There's a lot of ways you can say that, oh yeah, if I just, if I fix a natural number and just make that natural number bigger and bigger, this statement always works. But then when I start invoking infinity, if it goes all the way, your intuition might say, oh, if it works for an arbitrarily large natural number, it should work all the time, even up to infinity, and it turns out it doesn't, right? So you have a lot of these cases where you have some sort of counterintuitive thing that happens, but unless you see that specifically weirdly constructed counterexample, every easy thing you'll try will work, right? And I'll stress this again later, but this is why we don't prove things by example, because we have to show it's always true, not just true for the obvious cases. So let's just so the same thing. I'm just gonna, in this case, it's 3 statements, so I'll have 8 rows in my truth table. A little bit right out. Okay. So let's look at the first guy, right? So what are some pieces we need? We need P or Q. And then looking at the second guy, some pieces we need R and P. And we need R and Q, right? So these are fairly easy, right? At least one is true. The only time this is false is if both of them are false. So they both stop here and everything else is true. Up here, the only time that's true is when both of them are true. So if I look at R and P, they're both true up here. And they're both true up here. Oh, wow, I have grossly misjudged where my lines are, sorry. Okay, yeah, just missing another one here. So this is also true, but the rest are false, right? Finally, same thing for R and Q. I just want to look for the places where both of them are true at the same time, right? One down here, and the rest of them are false. Okay, so now let's look at this guy, right? Imagine we just extend it to this side of the board just because we're running out of space. And here I'll just, call this number 1, and this is number 2. Right. So if we look at this guy, we want R in this column. So that's easy to compare. We just look at this, right? So we want the cases where both these columns are true, and we get the first, the third, and the 5th row, right? But that's it. So we get the first, third, and the 5th. Right. Now, what about these last 2, right? We're just comparing this or this. Well, if they're both false, then this statement is false. So notice the last 3, this guy, right? Oh, wait, the only times that doesn't happen, the only times at least one of them is true is in the 1st row, the 3rd row, and the 5th row, which is exactly what we had on the left side. So you'll see that these 2 statements are logically equivalent because they have the same truth table, right? So that's, again, another way you can see or prove that these, so right now, obviously there's other ways to define these relations, and there's not always, you don't always say, okay, truth tables are the only way to prove these, right? We're only doing this because the definitions I gave you are based on truth tables, because is the needless to see at this point. There's a lot of books that will show you other ways you can define these, and you can certainly try to come up with them for yourself. But we'll stick with truth tables because that's what I define. It's easiest as an introduction to this topic, and it's easier to see when two things are the same, right? Like you see on the right side of the board. So it's pretty clear that those are the same statements. And you can obviously do the same thing if you flip these, if they're the same sign, blah, 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 right? There's a lot of things you can do with distributing these statements. So that should be good. Any questions on any of that? If you guys want to look up some properties of using logical connectors together, you certainly can. But these are kind of the most common ones you need. Anything else you need will either be super obvious or you can easily prove it. Right. Okay. But when I said on the so one of the homework assignments, or rather on, I think it's exercise 2 in problem set 2, I said, okay, here's a statement, write out a truth table and then give me a bunch of equivalent statements, right? Or write out 2 equivalent statements. So what I mean by that is, so far we've seen 2 ways of finding statements that are logically equivalent. We can use like kind of operations like we used to, right? We have these distribution kind of properties. Or maybe we can look at the actual truth table and say, okay, one way we can write this is use the rows that are true or the rows that are false to write down what my conditions are, right? So we've looked at a couple of different ways of showing how we can find logically equivalent statements from either basic operations or the truth table. Okay, so that's really all I want to say about the rest of propositional logic. And then now let's go ahead and finish up predicate logic. Let's see, yeah, I'm good at that. So this is still section 1.2. This is still on predicate logic. So we've introduced the ideas of quantifiers, right, and negation. Right? We talked about negating statements. We've talked about using quantifiers in every statement, and so on and so forth. We've talked about using formulas. But the question is, how do we do this when running, right? So one thing you will notice. So okay, for those of you who have taken a bunch of math classes before or are used to seeing math notation, you will probably have had one complaint or one thought in your mind as I was writing these statements out last class yesterday. And that would be, wait, you're not telling me where these things are. Sure, you're quantifying them, but you're not telling me where they're at. So for example, you know, a lot of people will see something written in the math class like, oh, for all x in R, right? So for all real numbers x, or something like that. I'll tell you what set this is in. But we haven't talked about sets yet, right? So again, I'm going to stress this whole thing of, well, we're going to try to build things from the ground up. We're not going to include things we haven't defined yet. And so, you know, we all know, most of us know what a set is. Even if you can't like write down formally what a set is, we still have an idea of what a set is, right? It's just a collection of things. So you usually expect me to tell you where these things live, and you will have seen this before. But notice I didn't do that, right? I did stuff like this, right? Or I did stuff like this, where I negated the statement by flipping it, right? I can even do compound statements. Maybe something like this. Right. Again, I'm going to note the same thing of, you know, if we say this in words, we are very likely to use commas in between, but you will notice a distinct lack of commas here. This is very typical when you see this written out in predicate logic, but you also know I'm not telling you where these things are, right? So for now, what we have to do is we have to create a universe that we live in, right? So for each of these statements, a statement lives inside a universe, right? Some people will use the word domain, and I do use that on the problem set that I gave out. You use the word domain. But for now, I'm going to stick with the term universe here. and maybe I'll change this for the problem set as well, because universe is a better word to use. The word domain is typically reserved for like functions or complex analysis. There's a lot of different definitions to the word domain that gets overused. So maybe I'll use universe here, but we have to define what universe we're in, right? So maybe I'll say that U is the universe containing all integers. For those of you who remember from problem set 1 or have done problem set 1, you know the integers can be written out as math blackboard Z, so I can write like this, right? I'll just tell you what the universe is. It's equal to this, right? The set of all integers. But again, don't worry too much about that since we haven't covered sets, so there's just one way of showing that, right? So if U is the universe of all integers, right, we can make a predicate. So anytime we want to talk about statements, right? So previously in propositional, we said, oh, P of X is maybe P is a statement that some number is prime, some fixed number, right? And I couldn't use just a variable X because, well, we haven't talked about variables in propositional logic. But now that we're in predicate logic, we can use that. So let's create a predicate for prime X. This is a statement that is prime, right? And we'll just assume the standard definition of prime, where a prime number is defined as one whose only divisors are one in itself. And you might ask, okay, what's the formal definition of divisor? Well, I don't want to go into too much into that. Well, that's something we can talk about when we talk about number theory. But for now, let's just use our standard, this stuff we've learned from high school and stuff like that, right? It's divisible. We just consider integers being divisible if you divide it and there's no remainder, essentially. I mean, that is a definition, right? You can definitely formalize that and nothing changes. It's not like when we move to the formal definition, we have to invoke some other stuff. It's just that once we talk about number theory, there's a lot of like sub-definitions that we need to talk about first before we actually say, okay, what exactly are we doing, right? How do we show something's divisible into another, and so on and so forth. And the reason for that is because for those of you who've taken algebra before, it's not always easy to say what dividing is, right? I always make the joke that even until you get to grad school as a PhD student in math, you still don't know what division is, right? Because we'll define multiplication and addition, and we'll define division as the opposite of multiplication almost, but a lot of times it's not well defined, right? So it's learning how to divide things is actually incredibly difficult if you're doing it forward. So anyway, let's go back to this predicate we're doing. And I'll just use that same example, right? Let's talk about primes and odd numbers, right? Right, so if I want to write a statement like this, I'll say that maybe, okay, so let's get rid of these examples. Let's start using actual concrete predicates. So I can say, within this universe, right, so I'll define a universe for this question, and then I don't have to reference the universe, right? Once you talk about what the universe is, we can just write out the statements. So for all X, we talk about and one thing we will do is we will extensively use parentheses instead of commas, right? So I don't want something like for all X prime X implies odd X without any quantifiers, right? So we use parentheses. But it's also good to remember that typically when we write these statements, we want to find a way to push all of the quantifiers to the left, right? So for example, maybe I could write something like for all X, blah statement is over here, implies there exists a Y, such as this statement over here. We can combine that by pushing the existential quantifier to the left before a single statement. So for now, we'll just work with our standard thing, but just remember that you might see stuff that doesn't look like there's a bunch of quantifiers for that one statement, but you can always rewrite it that way, right? So this statement is not true, right? Because 2 is a prime number, right? But a prime number is odd. I'm sorry, 2 is an odd, right? So we found a prime number that is odd, In other words, if you think about our truth table for this, we found a case where we're living in that second row where the hypothesis is true and the conclusion is false. All right, so this statement is false. But it's false in this universe. What do I change the universe? To say except 2. And maybe I'll say positive integers except 2, right? Because then again, like it's like, you can talk about negative integers being prime, we're not going to worry about that for now, right? And maybe here, for those of you who've seen set theory before, this, right? This just means without, we'll talk about that later, right? We'll talk about that in the set theory section. So if you haven't seen that notation, don't worry about it. So now this is true, right? I notice I rewrote my universe. I didn't rewrite the statement at all, right? I kept the same predicates. I kept the same statements, right? This is still perfectly fine now. So the whole point is when I write these out, it completely depends on what universe you're in, right? Whether this statement is true or false depends on the universe. That's going to be something you want to be careful about, right? So essentially, I'm not telling you where these are because when I say for all, I'm intrinsically saying for everything that already lives in this universe. When I say that exists, I mean there exists something from this universe, right? So that's implied in there. So when we talk about predicate logic, we have to be careful. So what if we want to restrict to something within the universe? Well, you're already seeing it, right? I'm restricting it to things in here. Because if I change my universe, right? Let's say, so let me just change this. I'll say that this statement is for this universe, right? Now let's pick a different universe. I'll call it U prime. And by the way, for those of you who haven't seen the notation before, when we use like derivatives, we'll say F prime, and we'll put this apostrophe up here. Sometimes we'll use prime just to indicate we want to use a letter that's the same for some reason, right? It's also a universe, so probably using the letter U is a good letter to use. But we want it to be a different thing, so we just add a prime to delineate it, right? Like it's nothing crazy. It's not like I'm taking a derivative of a set. Like that's not what I'm trying to do. It literally is just, okay, I want a different letter, but I want to use the same letter, so I'll add something to it, right? So that's something typical that we mathematicians do just to be lazy. So let U prime be the universe containing all primes except number 2. Then look. This is a true statement in this universe, right? In fact, this is the exact same statement as this up here. So essentially, this tells you that we can use implications to restrict to different parts of my universe, right? Like this may be a much simpler thing to say if I take the universe here, but if my universe is a lot bigger, then maybe I can restrict it to these things, right? So this looks different than this, but all that means is I'm only looking at the primes in this particular universe, right? If it's a prime, then it's odd, right? In the universe that gets rid of 2. So there's a lot of different ways to rewrite statements, and one of them is to just change the universe. Typically, we're not going to allow changing the universe because, like think about it, right? Well, that's ridiculous. I can't just say, oh, I'm going to change the universe right now to make myself right. Like, that's not how it works. So typically, if I'm living in some universe and my statement doesn't quite work, and I want to think about a universe that's a bit smaller, I can maybe put some conditions or create a new predicate to restrict myself, right? Now, you can't really go into a bigger universe. That doesn't make sense, right? You can't graph things that you don't know about. So this restriction thing helps to go back to the same universe, but our universes one of them must be contained in the other, right? So this universe as a set is completely contained within this set over here, right? So that's kind of the idea there. So it's important to define the universe, and it's important to look at, okay, when we take this for all, what do we do with that? I think I talked briefly about it last time, but I didn't exactly, what's it called? I didn't exactly give you examples, right? What happens when we combine quantiles? Something like that, right? I mean, if we read this out in words, it says, for every x in the universe, there exists a y such that blah, 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 right? Whatever all statements, right? And maybe if my universe is again all integers, then with z equals z, right? I can say that for every x, there exists a y, and then maybe I can create a predicate, right? So maybe I'll say, I'll find the inverse predicate. You know, you can think of additive inverses where they cancel out to 0 and stuff like that. You know, that makes sense. We'll see more of this in the algebra section, but we can say that we can create a predicate a comma b indicates a plus b equals 0. Right, so this is our predicate that we're creating. And again, we'll assume we know what plus is, we'll assume we know what equals is. In a vacuum, I wasn't allowed to write this, right? Because I haven't defined properly what any of this means. But for now, we're going to just assume it's the standard addition and standard 0 and so on and so forth, because we are living in the integers and we know how to add integers by like what we've learned before. So that's our predicate. Oh, one note here. So last time I used the term nth order predicate to talk about the number of arguments. That's how I've learned it before and seen it in other places. I did look at some sources after the lecture. So when I learned this, we talked about, you know, you can have nth order predicates, but nth order predicate logic means a different thing, right? So all we're talking about is what we call first order predicate logic. And then you can talk about second order predicate logic and blah, blah, blah. That's different than changing the number of arguments, right? So I've always thought it's a very confusing notation, but it turns out that people use like different words to describe that. So maybe first order predicate is not as accepted nowadays. So apologies for that. You can still use that term in your homework if you want, because that's what I'm used to and that's what I gave as definition. So as long as we've defined it that way, it's fine. But if you're reading books with predicate logic, some people use terms like unary, binary, basically n-ary, right? So like unary predicate means there's one. This would be a binary predicate because there's two. You can talk about 3-ary and so on and so forth. Right, so you can use that to describe the number of arguments. There's other words I've seen that are used to define the number of arguments in a predicate, but as long as you're clear on what's going on, it doesn't really matter, right? And if you define the predicate, it's obvious how many arguments come in there in the definition, right? Also, order matters. This always should follow a certain order. In this case, we happen to know that integer addition is commutative, right? A plus b equals b plus a, so we wouldn't have a problem here. But what if I define a predicate love that is defined as a loves b? Right? That's not the same as b loves a, right? So the order in your predicate always matters, and it comes in from how you define that predicate. So especially when you're talking about, you know, predicates with multiple arguments, especially you have to be careful about how you define it and what order you define it, along with what order you use it in, right? So let's see, going back to this. Okay, so using this, right, I can say, what if my statement is for all x, there exists a y such that, right? So how do we read this? We read this as, for every x, there is some y such that x plus y equals 0, right? I'm just following predicate. Or I can say this as x and y are inverses of each other, right? Additive inverses. right? And so here, pick an x, right? So this is arbitrary. So let me just pick a random number. There has to exist a y, right? So I can just say, oh, for every x, consider negative x. X minus x is 0 because x plus negative x is 0, right? So that when I say there exists a y, I'm just picking one, right? There only has to be at least one. There could be multiple. In this case, there isn't multiple, but there can be multiple. But I only have to pick one, right? This is something when we start talking about proofs and proof writing, that's something I'm going to harp on a lot, right? When I prove that there exists, I'll prove it by constructing it for the most part. But that's how that statement is true. What happens when we switch the quantifiers? Right, so for now, this is commutative, right? So if I switch these two, that doesn't matter, which means that if I swap these two variables, this is still the same statement. So really the only thing I've changed is I've swapped those two quantifiers. Is it still the same thing? Well, no, because what this says is there is an x somewhere such that no matter what y we pick, x and y are inverses. But that's obviously not true. Right? What this says is that there's a number where no matter what I add to it, I always get back to 0. But amongst the integers, that's not true, right? If I take 3, well, it has an inverse, negative 3. 3 minus 3 plus negative 3 is 0. But when I say for all y, it means everything, right? So I should be able to do 3 plus 4 equals 0, but that's not true. So we have to be very careful in terms of the order of the quantifiers, right? Changing the order of the quantifier changes a lot about the statements. And sometimes when you're reading these predicates, it gets to be a lot. It gets to be a huge chunk of things that you have to keep in your brain. But sometimes converting it makes a lot more sense, right? Just saying this in words will tell you what the difference is, right? If I'm just saying this in words, oh, for all x, or for each x, there is a y, or there exists a y such that x and y are inverses, versus there exists an x such that for all y, x and y are inverses, right? Once you say it like that, there's a very obvious difference between those, right? So that's what we have there. Okay, any questions there? Cool. So that's most of what I wanted to talk about regarding predicate logic. Let me think if there's anything else. So the idea is, when in the homework assignment, you might have to create your own predicates, but that's fine. Usually by convention, we use lowercase letters if we are like writing out a word versus uppercase letter if it's just one letter, right? Like we'll just say P of X, Q of X, right? But generally, we want to be as descriptive as possible, right? If you're relating two things or you're trying to say something, use a word, right? Like I don't say, use capital P of X and say X is prime. You can do that with propositional logic, but since we're using predicates, try to use like a word followed by something in the parentheses, right? And remember that, you can be creative. You don't just have to have one argument. You can create as many arguments as you need, right? So, I kind of hinted at this in the homework set. But one of you was asking for, we were talking yesterday about those stupid problems like, oh, Mary is in front of John, John is between these two people, this person's like fourth in line, blah, blah, blah. We can create predicates to simulate that, right? We can maybe create a predicate that says, well, hi, right? That says A is behind B. Or we can create a predicate that says between, and it's a 3-array predicate, and this says X is between Y and Z. Well, I could define it that way. You can also make it defined so that it makes a lot more sense. You can define this as Y is between X and Z, so you can literally see that it's in between, right? So you can define your predicates however you want in a way that makes it easier for you to keep track of what you're talking about. But at the end of the day, you have to define your domain, or rather your universe, and you have to define your predicates. And then from there, everything's the same as what we talked about, right? So you'll be able to put that together in some way. And now that we've written it in predicate form, it's a lot easier to negate, right? So maybe negating this statement would be a lot harder if I'm just looking at the English, right? What's the opposite of for every x there exists a y such that x plus y is 0? Well, once you convert it to this statement, it becomes very easy to negate. I can just say, oh, there exists an x such that for every y, x and y are not inverses, right? I immediately see this from flipping everything, flipping every quantifier, negating the statement at the end, right? So again, that's why we use predicate logic. That's why I stress this so much, because rewriting everything using predicate logic becomes second nature once you've done it for a while. And once you do this, it becomes very easy to negate statements. As we go on in the course, I'll stop saying predicate logic and stuff like that. I'll just say, oh, write everything in terms of quantifiers, right? What I mean by that is just write everything using predicate logic. And you can kind of relax this, right? If we're strictly living in the world of predicate logic, there's a specific way in which we should be writing things. But later on, we can maybe change this. And when we're just talking about statements, we can say that, oh, for every x and r, we can say there exists y and z such that y plus z is greater than x, or something like that, right? Notice I'm no longer creating my predicate first and sticking it here. I'm no longer creating a predicate that represents a certain statement and putting it in here. I'm just kind of like rewriting it in words. You can even use the word for all, right? But the idea being that no matter how you write your statement, this is perfect. This is what we're going to end up, writing. This is what all our statements are going to end up looking like. The idea being that we still have the same format where I have a quantifier here, I have a quantifier here, and then I have a single statement at the end, right? This is basically what we're using predicate logic, right? I want to formalize predicate logic by teaching you how to create these predicates and teaching you how to get these quantifiers. But at the end of the day, when we relax from predicate logic and we're just looking at general, speech and general question, we can still use the same idea, right? Maybe if I have a bunch of statements kind of scattered throughout this, I still can rewrite it in the same way where I push all the quantifiers to the beginning and then just have my statement at the end. Right, that makes sense? Right, cool. So that's kind of the idea, right? So what I'm doing right now is we're, like I said, we have to start from somewhere. So we've defined propositional logic, we've defined predicate logic, we've talked about some ways we can put together things within propositional and predicate logic. And so now we have a language, right? That's what I said on day one, right? We need a language. We need a way to talk. We need a way to use grammar and vocab. Well, here's our grammar, right? Now we know how to put statements together. And once we know how to put statements together, we just need to build our vocab, right? So we build our vocab, we'll start talking more about more definitions. We'll start learning different ways in which we can talk about mathematical objects. And once we talk about mathematical objects in a certain way, now we can use our grammar to figure out why certain statements are true or false. So any questions? Okay, so I think I'm gonna go ahead and end early, about half an hour early, because I think that's probably a good starting point. Yeah, so that's pretty much all I wanted to say about predicate logic. So we've got propositional logic, predicate logic. I'm pretty much gonna stop there. And then tomorrow, I'm going to briefly talk about some proofwriting techniques. We're not going to expand on them too much because I still want to talk about some set theory before we really dive into actually being able to prove things. But we'll go ahead and talk about some types of proofs and what you might expect to how to prove things now that we've talked about kind of grammar rehydrating, right? So what are some ideas you want to think about? What are some ideas in proofwriting? How I want you guys to start writing proofs if you're new to it, and so on and so forth. So if there's no questions, I think that's going to be good for today.